All right. We are going to be looking at some important derivations that we are going to use to solve some numericals on this flinge beam. All right. So, and here is a flinge beam. We have already discussed what a flinge beam is. We have discussed the concept of a flinge beam in our introductory class. So you can click on the link on the screen, or you can just search for introduction to flinge beam on our playlist. We are going to get it. All right. So now we are going to be deriving some important concepts, and I will just brush through it. All right. So the first thing you need to note here is what a flinge beam is. We've said a flinge beam is basically a composite material that comprises majorly of what? Of a wooden beam or timber and a what? And a steel plate or steel for the purpose of sharing load. All right, so this is a perfect example of a what? A flinge beam. You can see a wood here, and all of this stuff is a fiber in the wood, and here is two steel that is attached, that is bolted alongside the wood. And the purpose of this is for them to share load, and the purpose is also for us to increase the load capacity of the what? Of the wood. All right. So yeah, we are going to be looking at some important assumptions. The first one is the load. The strain in the steel must be equals to the strain in the what? In the wood. Strain. The first strain in steel is equals to strain in wood. All right. So, and you are going to recall from your Hooke's law, we said that our stress is directly proportional to what? Strain. So for us to remove this sign, we are going to say stress is equals to, then we are going to input a constant, which is what? Modulus of elasticity. All right. So this is our stress, this is our strain. So if we make strain the subject here, that is, we are going to divide both sides by E. So it shows that strain will be equals to stress all over what? Young modulus. So here we are saying strain in steel will be equals to what? Strain in wood. All right. So it shows that our strain here is stress over what? Modulus of elasticity. So the strain in steel now, we are just going to denote it with, we are just going to put S here, S here. So we are going to say stress here, the stress in steel all over the modulus of elasticity in steel will be equals to the stress in wood all over what? The modulus of elasticity in wood. All right. So the next thing you are going to take note here is this. If we make our stress in steel the subject, we are going to have this to be equals to what? So the stress in steel will be equals to the modulus in steel, modulus of elasticity in steel all over the modulus of elasticity in wood multiplied by what? Multiplied by the stress in wood. All right. So you are going to note that we are going to replace this ratio with E and sorry, with M, and we are going to denote our M to be what? Modular ratio. So you are going to know that M is equals to the stress, the modulus of elasticity in steel all over the modulus of elasticity in wood, and where our M is known as what? Modular ratio. All right, so if we do that, we are going to have our stress in steel to be equals to what? M multiplied by what? Stress in wood. So take note of this. All right, so you have to take note of that, and you're also going to note that this modular ratio is also greater than 1. You have to take note of that. You have to know that modular ratio is greater than 1. All right, so the next thing you are going to take note here, the next assumption here that you are going to take note here is, we said that the purpose, one of the purpose of this flinge beam is for us to increase the load capacity of the wood, and I've already told us that basically that our steel here must take more load, more than the what? More than the wood. But yeah, we are going to assume an assumption here that the load share by steel is equals to the what? The load share by wood. All right. So we are saying load shared by steel is equals to the load shared by what? By wood. All right, so you are going to take note of something here, that from the formula of our stress, we know that stress is equals to what? Load all over what? Area, right? So if we make our load the subject here, we are going to have load to be equals to stress multiplied by what? By area. So here we are going to have load share by steel. Now it's going to be stress of the steel multiplied by what? The area of the steel. So we are going to have stress of steel multiplied by area of steel, which is going to give us what? The stress of the wood multiplied by the what? Area of what? Of the wood. All right. So now you are going to note something carefully here again, that the area of the steel, now you are going to take note that the area of the steel here, the steel is just a rectangle in nature, right? So it's going to be what? The base of the steel multiplied by what? Multiplied by the depth. All right. So here we are going to have the stress of the steel multiplied by, now we are replacing our area now. The area of the steel now is going to be what? The base of the steel multiplied by what? Multiplied by the depth of the what? Of the steel, which is going to be equals to the stress of the wood multiplied by what? The base of the wood, then multiplied by what? By the depth of the wood. All right. So now the next thing you are going to take note here is that the depth of the steel and the depth of the wood, they are the same. You can see depth here, right? So for the steel, from this point to this point is depth. For the wood too, from this point to this point is also depth. So you are going to note that ds is, that is, the depth of steel is equals to what? The depth of the wood. So it shows that this will go with this. So we are going to be left with what? We are going to be left with the stress of the steel multiplied by the base of the steel, which is going to be equals to the stress of the wood multiplied by what? By the base of the wood, right? All right. So we can decide to divide both sides by the stress of the wood and the base of the steel. So here we are going to have this to be equals to, so we are going to have stress of wood multiplied by the base of steel. We're going to have stress of wood multiplied by the base of steel. So here, the base of steel here, the base of steel will go with the base of steel, and the stress of the wood will go with the stress of the wood. So here we are going to have the stress of the steel all over the stress of the wood. This will be equals to base of the wood all over what? The base of the steel. So I hope you understand that. All right. Now, but you are going to take note of something carefully here, that the base of the steel is in what? Thickness. So we have two steel here. So it shows that the base of the steel is equals to 2t. So we can also replace this formula with, we can also say this formula is the stress of the steel all over the stress of the wood will be equals to what? It's going to be equals to the base of the wood all over what? All over 2t. So you can also have this. So take note of that. So now, what will now be the total load? What will now be the total load? All right, so the total load of the flitched beam now, the total load of the flitched beam will be equals to, let's put T total here. Please take note, this is total load. So this will be equals to, the load of the what? Of the steel plus what? The load of the wood. That is load of steel plus what? The load of what? Of the wood. So which is going to be, since we know our load, here the load of the steel is just what we have here, and the load of the wood is just what we have here. So you can further rewrite this to be stress of steel, then the base of the steel, which is 2 thickness, plus the stress of the wood, then multiply by the base of what? Of the wood. All right. So this will be the total load. So this will be the formula for the total load. All right. So I'm going to clean. You can quickly take a screenshot. So the third point here is they have the same radius of curvature. So for us to do this, we are going to recall from our Flitched equation that says that we have m over I. This will be equals to what? It's going to be equals to E all over what? All over R. I'm sure you know what all of this is. All right. So our M here is our maximum bending moment. Our I here is our moment of inertia. Our E here is our modulus of elasticity, while our R here is the radius of curvature. So if we make R the subject here, our R will be equals to what? R will be equals to M all over what? All over E I. So it shows that the radius of curvature of steel now is going to be equals to the radius of curvature of wood. So we can say that M is the moment, that is the maximum bend moment of steel, all over the what? The modulus of elastic modulus of steel, then the moment of inertia of steel will be equals to the maximum bending moment of wood all over what? All over the modulus of elasticity of wood, then multiplied by the moment of inertia of wood. All right. So that is it. So the fourth thing that you need to note here is the total bending moment. So let's go for the total bending moment. Total bending moment. All right. So the total bending moment of a flint beam is denoted with what? M. So you can just put T here. So this will be equals to the bending moment of the steel, bending moment of steel, plus what? Plus the bending moment of wood. So that is what we are going to have. All right. But we are going to perform some analysis here. All right. So you are going to take note. Now, you are going to recall again from Flitched equation. If we have M all over I, this will be equals to what? Stress all over what? Y, right? All right. So if we make, okay, no need to make anything the subject here. And you're also going to recall that our Z here, our Z, I hope you still know what our Z is. So our Z here, that is the section modulus. So if I'm coming, okay, let's say our Z, you know our Z, but I don't want to write a lot of notes here. Just want to go straight to the point. All right, our Z here, okay, this can be equals to, let's make our M the subject. So we can write our M to be equals to I all over Y, then multiply by stress. And then you are going to recall that our Z is nothing but what? I over what? Y. So we can say that our M is equals to what? Stress multiply by what? By Z. All right. So that is the first thing you need to take note there. All right. So we are going to be applying two things here. First, we are going to be taking our bending moment to be stress multiplied by what? Section modulus. And the second, we are going to do all the analysis and we are going to take our second assumption to be I over y multiplied by what? By stress. All right. So the first one, if we take our bending moment to be stress multiplied by section modulus. So for this T, it shows that we are going to have our bending moment for this T to be what? To be stress of this T multiplied by the section modulus of this T. And again, for the wood, we are going to have bending moment of wood to be stress of the wood multiplied by what? The section modulus of the wood. All right. So let's substitute this there into the total bending moment formula. So this will be equals to stress of the steel multiplied, that is multiplied by the section modulus of the steel plus the stress of the wood, then multiplied by the section modulus of the wood. I hope we get this. All right. So now the next thing you need to note here is what is the section modulus of the steel and what is the section modulus of the wood. If you look at this shape, for the steel is rectangular in nature and the wood is also rectangular in nature. So you are going to recall that the formula for the section modulus of a rectangle will be used here, and which is nothing but what? BD square all over what? 6. So here it shows that here we are going to have this to be equals to stress of the steel multiplied by BD squared all over what? 6. But everything here is going to be what? S plus the stress of the wood multiplied by what? BW multiplied by DW squared all over 6. I hope we understand this. All right. So the next thing you are going to note here is this. From our first assumption, we said the strain in the steel must be the same as the strain in the wood, right? So, and then we proved that, we said that the strain in the steel will be equals to modular ratio multiplied by what? Multiplied by the stress in the wood. All right. We showed that the stress in the steel is equals to modular ratio multiplied by the stress in the wood. So if we substitute that here now, we are going to have our formula here to be written in form of modular ratio multiplied by the stress in the wood, then multiplied by B subscript S, D subscript S all square over 6 plus what? Plus stress in the wood multiplied by B subscript W multiplied by D subscript W all square over 6. All right. So now, don't forget again that they are having the same depth, right? They are having the same depth. That is, the depth of the steel is the same thing as the depth of the what? Of the wood. So we can say that DS is equals to DW. So I'll have to clean up. We said they are having the same depth. So let's just equate this. Let's just equate everything to be equals to D. All right. So we are going to substitute D for everything there. So we can say that our total bending moment, or you can call it moment of resistance, will be equals to, this will be equals to M, that is the modular ratio, multiplied by the stress of the wood, then multiplied by the base, then multiplied by D squared over what? Over 6 plus stress of the wood, and then multiplied by the base of the wood, then D squared, everything over what? Over 6. All right. Now, you are going to recall carefully that the base of the steel, we are having two steel. Then their base is T, right? That is the thickness. So we are going to have 2T. So the base of the steel is equals to 2T. So we are going to replace what we have here with 2T. So B subscript S is equals to 2T. So if we substitute that here, we are going to have this to be M multiplied by the stress of the wood. Then we are going to have 2T here. We're going to have 2T Then we're going to have depth, everything over 6 plus the stress of the wood, then the base of the wood, then depth, the depth to the power of 2, everything over 6. All right, so this will be equal. So if you look at this, something is common, right? We can factor out the stress of the wood. So if we factor out the stress of the wood, then we'll be left with what? We'll be left with our modular ratio multiplied by the thickness, that is 2t multiplied by m, then plus what? Plus, here we are going to be left with the base of the wood. Then we can factor out depth squared all over 6. All right, so this is what we are going to have. So everything here is equals to B equivalent. So everything here is B equivalent. So this will be equals to, let's say, B equivalent B equivalent. All right, so this will be equals to 2t m plus B subscript W. All right. All right, so because there are sometimes you can be asked to calculate B equivalent. So this is the formula for B equivalent. All right, so and what this concept is explaining to us is this: the moment of resistance of the flitched beam is same as the moment of resistance of the wood of the same depth, but of width, which is equals to what? 2tm plus what? B subscript what? W. Please take note of that. The moment of resistance, you can see some question when you are preparing for some examination like GATE. You are going to see that which of the following statements is true. The moment of resistance of a flitched beam is same as that of a wooden beam of the same depth, and but the width is 2tm, that is 2 multiplied by thickness multiplied by what? The modular ratio plus the base of the what? Of the wood. So this is what we deduce out of there. So please take note of all of this, both theory and the proving. You can be asked to show all of this mathematically, and this is how to go about it. So now we are still under this case here. Now, what of if we are taking our m now to be equals to Iy multiplied by stress? So what is it going to look like? All right, so now let's do that. Now we are just going to start from here. I'm going to start from here. I think m subscript t should be equals to the bending moment of the steel plus what? Plus the bending moment of what? Of the wood. All right, so if we are taking our bending moment to be this, so it shows that the one of steel, we're just going to put s here, right? So we are just going to have here to be I subscript s multiplied by C subscript s, that is stress subscript s all over y subscript s plus I subscript w multiplied by stress subscript w all over y subscript what? W. So this is what we are going to have. All right, so now the next thing we are going to do, for us to continue, I will have to clean. So now you are going to note carefully here that we already have a formula for our stress of steel, which is modular ratio multiplied by the stress of what? Of the wood. So we are going to substitute that there, and again you are going to note that this y here is y max, that is the distance from the neutral axis to the what? To the top part of the what? Of the section. And this is same for both the steel and what? And the wood. So you can see that y subscript s can see that y subscript s is equals to y subscript w. Everything is equals to what? Y. And you're also going to note that our stress of the steel is equals to modular ratio multiplied by stress of what? Of wood. All right, so if we substitute all of that stuff there, we are going to have our m subscript t to be equals to, so this will be equals to I subscript s multiplied by what? Multiplied by our stress, which is m multiplied by stress subscript w, everything here over y, plus here we are going to have I w multiplied by our stress here, everything all over what? Y. All right, so something is common here. So if we factor that out, we are going to have stress in the wood all over y into, then we are going to have is m plus what? Plus iw. So here this is called I equivalent, that is the moment of initial equivalent of the section. All right, so you have to take note of all these derivation. We are going to be applying them in our subsequent lectures. We are going to be using them to solve series of problems. So we are going to note that I equivalent is equals to I subscript s m plus I w. So all right, so this is everything that you need to take note in this derivation. So here are all the important derivations you need to take note. So if today is your first time of coming across our content, please do it to subscribe and hit the notification bell so that each time we upload video like this, you'll be the first to receive the notification. And don't forget to click on the join button to join our membership group. There you are going to have access to member only video. You have access to chat with us, communicate with us, ask questions of any kind that you are having challenges with. And please do where to share this video with your friends who might be in need of it. So stay tuned for more, and stay tuned for more and more numericals on Flitched Beam. We are going to cover every aspect of every examination. Thanks.